Cosmology, the story of the universe from beginning to end. Imagine looking up at the night sky and asking the simplest, most profound question imaginable. Where did all of this come from? That single question has guided humanity for thousands of years, and today, it forms the foundation of an entire scientific discipline. Cosmology is the study of the universe as a whole, examining how it began, what it is made of, how it changes over time, and what may happen in the far future. Unlike most sciences that study particular phenomena within the universe, cosmology is unique. It studies a single object, the entire universe itself. Every observation, every measurement, every theory contributes to our understanding of this one grand structure that encompasses everything we can observe. The word cosmology itself carries deep meaning in its roots. It comes from two ancient Greek words, cosmos, meaning the ordered universe or world, and logia, meaning the study of. The Greeks used cosmos to describe not just the physical universe, but the idea of an orderly, harmonious system, standing in contrast to chaos. When we practice cosmology, we are continuing a tradition that stretches back millennia, seeking to understand the fundamental order that governs all of existence. By studying the universe on the largest possible scales, cosmology allows scientists to test the most fundamental laws of nature. These are the laws that govern gravity, space, and time themselves. In a very real sense, cosmology is the science that asks the biggest questions and seeks answers at the grandest scale imaginable. Modern cosmology rests on a revolutionary foundation laid by Albert Einstein in the early 20th century. His theory of general relativity describes gravity not as a force pulling objects together, but as something far more elegant, the curvature of space and time itself. Massive objects like stars and galaxies bend the fabric of space-time around them, and this curvature guides the motion of everything around them. This framework has been tested and confirmed through countless observations made by telescopes on Earth and in space. These instruments scan the universe across the entire electromagnetic spectrum, from radio waves to gamma rays, revealing structures and phenomena that would otherwise remain invisible to us. The prevailing model that emerged from these observations is known as lambda-CDM. This model describes a universe composed of three main components: ordinary matter, the stuff that makes up stars, planets, and ourselves; dark matter, an invisible substance that interacts only through gravity; and dark energy, a mysterious force causing the universe to expand at an accelerating rate. Now, let's return to the beginning. The leading theory describing the origin of our observable universe tells us that about 13.8 billion years ago, everything we can see existed in an extremely hot, dense state. This moment, often called the Big Bang, marks the beginning of time as we understand it. But the Big Bang was not an explosion in the way we typically imagine explosions. It was not matter flying outward into empty space. Instead, it was the expansion of space itself. Space, time, matter, and energy all emerged together, expanding outward from this initial state. As space expanded, the universe cooled. In those first fractions of a second, the universe was far too hot for even atoms to exist. But as temperatures dropped, the first simple particles began to form. Quarks joined together to create protons and neutrons, the building blocks of atomic nuclei. During the first few minutes after the Big Bang, the universe was still extraordinarily hot and dense. Nuclear reactions occurred, fusing these protons and neutrons together to create the first atomic nuclei. Hydrogen formed first, being the simplest element, then helium and trace amounts of lithium. These were the only elements created in those first moments. Every other element we know, from carbon to iron to gold, would have to wait for stars to form. After about 20 minutes, the universe had cooled enough that nuclear fusion could no longer occur. But the universe was far from finished transforming. For hundreds of thousands of years, it remained a hot, opaque plasma. Free electrons and atomic nuclei moved independently, scattering light in all directions, making the universe effectively foggy. Then, around 380,000 years after the Big Bang, something remarkable happened. The universe had cooled enough for electrons to combine with nuclei, forming the first neutral atoms. This moment, called recombination, changed everything. With neutral atoms now formed, light was finally able to travel freely through space. The fog lifted. The universe became transparent for the first time. That first light, released when the universe became transparent, still exists today. We call it the cosmic microwave background, or CMB. As the universe has expanded over billions of years, this light has been stretched to longer wavelengths, shifting from visible light into the microwave portion of the spectrum. The CMB fills all of space around us. It has an almost perfectly uniform temperature of about 2.7 Kelvin, just a few degrees above absolute zero. But within that near-perfect uniformity lie tiny variations, temperature differences of just a few millionths of a degree. These tiny variations are extraordinarily important. They reveal density differences in the early universe, regions where matter was slightly more concentrated than in others. Over time, gravity amplified these small differences. The denser regions attracted more matter, eventually growing into galaxies and vast clusters of galaxies. The CMB is, in essence, a baby picture of the universe, showing us the seeds of all cosmic structure we see today. The discovery of the CMB in 1965 was a watershed moment in cosmology. Two radio astronomers, Arno Penzias and Robert Wilson, detected this faint microwave signal coming from all directions in the sky. They had found direct evidence that the universe had once been far hotter and denser. This discovery remains one of the strongest pieces of evidence supporting Big Bang cosmology. Modern satellites have mapped the CMB in exquisite detail, revealing its subtle patterns across the entire sky. These patterns allow scientists to measure fundamental properties of the universe: its age, its shape, and its composition. The universe, we now know, is remarkably flat, extending in all directions as far as we can observe. Understanding that the universe is expanding required a crucial observation made in the 1920s by Edwin Hubble. Using the largest telescope of his time, Hubble studied distant galaxies and made a startling discovery. Nearly all of them were moving away from us. More importantly, he found a pattern. The farther away a galaxy was, the faster it appeared to be receding. This relationship, now called Hubble's law, revealed something profound about the nature of space itself. The expansion Hubble observed does not mean galaxies are flying through space like debris from an explosion. Rather, space itself is stretching. Imagine dots on the surface of a balloon. As you inflate the balloon, the dots move apart, not because they're moving across the rubber, but because the rubber itself is expanding between them. Similarly, galaxies move apart as the space between them expands. This discovery also implied something remarkable about the past. If the universe is expanding now, it must have been denser in the past. Running the expansion backward in time leads inevitably to that hot, dense state we call the Big Bang. Yet, as astronomers studied galaxies more closely, they encountered something unexpected. When they measured how fast stars orbit within galaxies, the speeds didn't match what gravity should produce based on the visible matter alone. Stars at the edges of galaxies were moving far too quickly. According to the laws of gravity, they should fly off into space, yet the galaxies remained intact. Similar observations of galaxy clusters showed the same problem. The visible matter could not account for the gravitational effects being observed. Something invisible was providing additional mass, holding these structures together through its gravitational influence. Scientists call this invisible substance dark matter. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation in any way we can detect. Yet it interacts gravitationally, and its presence is revealed through the motions of visible matter. Dark matter makes up roughly 26 to 27% of the universe's total energy content. That means there is more dark matter in the universe than ordinary matter by a significant margin. It acts as a cosmic scaffold, providing the gravitational framework around which galaxies and galaxy clusters form. Despite decades of research, the true nature of dark matter remains one of cosmology's greatest mysteries. Experiments around the world continue to search for its particles, but so far, dark matter has revealed itself only through its gravitational effects, never through direct detection. If dark matter was surprising, the discovery made in the late 1990s was astonishing. Astronomers studying distant supernovae, stellar explosions that serve as cosmic distance markers, expected to find that the expansion of the universe was gradually slowing down. After all, gravity should work to pull everything back together, gradually decelerating the expansion. Instead, they found the opposite. The expansion of the universe was not slowing down. It was speeding up. To explain this acceleration, cosmologists introduced the concept of dark energy. Unlike dark matter, which clumps together and pulls things gravitationally, dark energy appears to be smoothly distributed throughout space itself. It exerts a kind of repulsive effect, pushing space to expand faster and faster. Dark energy makes up about 68% of the universe's total energy content. This means that more than 2/3 of the universe consists of something we do not understand. We do not know what dark energy is, where it comes from, or why it has the properties it does. The most common explanation is that dark energy is a property of empty space itself, a kind of energy inherent in the vacuum. Einstein's equations of general relativity actually allow for this possibility, represented by what he called the cosmological constant. Interestingly, Einstein initially introduced this constant for different reasons and later considered it a mistake. It may turn out to be real after all. These discoveries about dark energy and the accelerating expansion lead naturally to questions about the future. What will happen to the universe over cosmic timescales far beyond our own lifetimes, or even the lifetime of our sun? If dark energy remains constant, as current observations suggest, the universe will continue expanding forever. This expansion will accelerate, carrying distant galaxies farther and farther away from us. Eventually, billions of years in the future, galaxies beyond our local group will move so far away that their light will never reach us. They will pass beyond our observable horizon. Stars will eventually exhaust their fuel. New stars will stop forming as the available gas becomes too dispersed. The universe will grow darker and colder, a process that will unfold over trillions upon trillions of years. Alternative possibilities exist. Dark energy might not remain constant. It could change over time, either strengthening or weakening. Some scenarios predict a big rip, where dark energy becomes so powerful it tears apart galaxies, then stars, then planets, and eventually even atoms themselves. Other scenarios suggest the universe could eventually stop expanding and begin to contract, leading to a big crunch. However, current observations favor the scenario of ongoing accelerated expansion. The universe appears to be headed toward a cold, sparse, and very distant future. Despite tremendous progress, cosmology still faces profound mysteries. We have names for dark matter and dark energy, but names are not understanding. We do not know what dark matter particles are, if they exist at all. We do not know why dark energy has the strength it does, or whether it might change over time. And then there is the question of the very earliest moments. General relativity breaks down at the extreme conditions present at the Big Bang itself. We need a theory that unites quantum mechanics with gravity to understand what happened at the very beginning, and such a theory remains elusive. Some theories suggest that our universe may be just one among many, part of a vast multiverse where different regions have different physical laws. These ideas push the boundaries of science into realms that are difficult or perhaps impossible to test observationally. Yet this is precisely what makes cosmology so compelling. It stands at the intersection of observation and theory, of the known and the unknown. Every question answered reveals new questions to ask. Cosmology matters because it places humanity in context. For most of human history, we believed Earth was the center of everything. Then we learned we orbit an ordinary star. Then that our star is one among hundreds of billions in a galaxy. Then that our galaxy is one among hundreds of billions of galaxies. Now we understand that we exist 13.8 billion years after the beginning of time, in a universe mostly composed of things we cannot see, on a trajectory toward a future so distant we can barely conceive of it. And yet, we are here, capable of observing all of this, capable of understanding it. We are, as far as we know, the universe's way of knowing itself, of reflecting on its own existence. In studying the universe, we are studying the deepest laws of reality itself. We are asking the questions that have driven human curiosity since the first person looked up at the stars and wondered. And though the answers continue to reveal new mysteries, the search itself connects us to something far larger than ourselves, the vast, expanding, ancient cosmos that gave rise to us, and that we, in turn, strive to understand.